In this brief lesson, we'll cover bond polarity and the bonding continuum. We'll accomplish this by relating electronegativity to bond polarity so that we can classify bonds as ionic, polar, or nonpolar. Let's begin. When you have a diatomic molecule made up of the same two atoms, the electrons will be shared evenly, as in the fluorine molecule at the bottom right. We would classify the fluorine-fluorine bond as being nonpolar and purely covalent. If we look at the molecule of hydrofluoric acid, though, we see a huge electronegativity difference between the hydrogen and fluorine. As a result, the fluorine pulls more of the electron density towards itself, resulting in a partial negative charge on the F atom, as indicated by the delta minus symbol, and a partial positive charge, delta plus, on the H atom. These positive and negative poles in HF indicate a charge separation and some level of ionic character. Large differences in electronegativity, delta En, between atoms indicate uneven sharing of electrons and perhaps even the transfer of electrons to form ionic bonds. Moderate delta En values indicate less even sharing and polar covalent bonds, where the most electronegative element is always the negative pole. Small delta En values are associated with slightly unevenly shared electrons and slightly polar covalent bonds. The only true nonpolar bond exists when the two atoms have exactly the same electronegativity. Let's classify some molecules to practice. Using the electronegativity values provided, calculate delta En so we can rank the molecules from most to least polar. We find that HF is the most strongly polar, while HCl and HBr are similar in polarity, with HCl being perhaps a bit more polar. HI is the least polar of the molecules listed. Bonds between atoms can range in type from nonpolar covalent, evenly shared electrons, to polar covalent, unevenly shared electrons, to completely transferred electrons in ionic bonds. Note that the nonpolar covalent side of the spectrum represents 100% covalent bonds, so there are no partial or full charges indicated. Our polar covalent molecule forms dipoles, as indicated by the partial positive and partial negative symbols on either side of the molecule, and will have some ionic character. A molecule doesn't become an ionic formula unit, though, until the electrons are completely transferred, resulting in full positive and full negative charges, as indicated on the ionic compound. As chemists, we like to be able to quantify every observed phenomenon. The dipoles found in polar covalent bonds are no exception. Dipoles exhibit separate areas of opposite charge of equal magnitude. We measure them using the dipole moment, mu, which relates the magnitude of the charge, q, and the distance between the charges, r, and is reported in debye units, d, where 1 debye equals 3.34 times 10 to the negative 30th coulomb meters. While I'd like for you to be familiar with this unit and the parts that make the calculation possible, we will not do any calculations with this formula this semester. As always, I'll leave you with the parting thoughts of the authors.